Hi there, guys. We're going to look at kinematics today. And kinematics is basically the relationships between displacement, velocity, zoom out, velocity and acceleration. It's got nothing to do with forces, so don't worry about that if you've been dealing with some forces in physics. It is basically using calculus to connect up displacement, velocity, and acceleration. You probably know already that velocity, or speed rather, is distance over time, average speed that is. So it shouldn't come as a surprise really that velocity is equal to your change in displacement divided by your change in time, or in other words, ds dt. But obviously this is a situation where we're looking not at average velocities, we're looking at gradients on curves. A gradient on a displacement time graph would represent velocity. Likewise, the change in velocity over time is called acceleration. Differentiate velocity with respect to time, get acceleration. Guys, I'll come up with just a brief example of this. So if we're talking about like 100 meters sprint, so over time, we're talking displacement over time, it takes 15 seconds. And we've got 100 meters. Maybe we start with a certain, come out of the blocks with a certain acceleration speed already, and it gets faster and then slows down a little bit, but we still keep going at the end. That's meant to be at 15, 100. And maybe at, let's say, 9 seconds here, we have our fastest speed. Speed, or displacement, obviously having direction as well. We're going in the positive direction down the track. So at this place, we have the steepest gradient, and that represents the fastest speed. Okay, so your gradient is representing speed there, basically. That's all I really wanted to say. If you wanted to change that into a velocity time graph, now this looks like a cubic. So when we differentiate that, we'll get a quadratic. At 9 seconds, we'll have the highest point here, and 15 seconds somewhere up here. And I don't know, maybe the fastest speed is 12 meters per second. I'm just sort of guessing at that. There's time, my 0 in the corner. And maybe the velocity already started at a certain speed, certain pace, if you like, speed. And then it comes down to something like this. So this would be saying, well, we come out of the blocks with something like a velocity of 4 meters per second already. And we finish the race at something like 8 meters per second. So there we go. That's what the velocity time graph would look like. Now, the acceleration time graph is one which normally confuses people a little bit. We have what's happening here? So we have an acceleration in the first part. So we're accelerating, we're getting faster and faster to the middle. So the velocity is increasing, so that means we've got a positive acceleration there in 9 seconds. So velocity is increasing, but it's increasing less and less until we get to that top part. It's the rate of change of the velocity is decreasing. So the acceleration is still positive, but the rate of change of the acceleration is decreasing. So what do I mean about that? So I mean, I was looking at the next derivative after that. So what I mean is that it starts off with a high increase in the velocity, because we can see it's quite steep here, and then it becomes less steep. So the acceleration goes down to 0 at 9 meters per second. That's where we're flat. So the derivative of this curve is going to give us 0 gradient at the top. Okay, and at this point here, we are now decreasing to this point. The velocity is going down from 12 to say 8. So that means a negative acceleration. So, and it gets more and more. The velocity, the language is difficult here. The velocity increasingly reduces. So it looks like this. Okay, now if we differentiate a quadratic, we're going to get a straight line graph, and the straight line graph is going to look something like this. Now, I don't know what the numbers are on the side here, but I know obviously that's 15 seconds there, and then we start at 0. So the acceleration time graphs are always quite tricky to draw, in fact. Okay, anyway, the most important thing is that you understand that the ds dt equal to v, and dv dt is equal to a, but also you could say that the second derivative of your displacement is also your acceleration. Now, if you want to go backwards through these things, of course, if you integrate your acceleration with respect to your velocity, and if you integrate your velocity with respect to time, you will get your displacement. You will just need a plus c in most of the questions when we deal with those things. Okay, so let's have a look at this question. Okay, so example 19. Okay, so this one's saying a stone is thrown vertically upwards. So we're talking about this thing going vertically upwards, and then it comes downwards, and it goes past 2 meters above the ground before it hits the ground again. It has an initial velocity going upwards of 4.9 meters per second. And so that's meters per second, by the way, that's the same as saying meters per second like this. Yeah, okay, so if you're going to draw the velocity, we say the displacement time graph in this case, it's going to look like something like this at 2 meters there. And because with respect to time, it's going to look like it's going sideways. So something like this. And I think it's going to be a quadratic. Okay, so we'll show that in a second as well. Okay, so there's some important information in this question. Initial velocity means, you can write this down if you want at the start of the question, when t is equal to 0, v is equal to 4.9, and also s equal to 2. So that's a good bit of information which is going to help us find our formulas. Okay, now I don't have a quadratic formula for my displacement time graph. I don't know what that is at the moment. I don't have a formula for my velocity. I do know that my acceleration is fixed, and my acceleration, I haven't read it out just yet, but my acceleration is here. So the acceleration is due to gravity. The velocity is changing by minus 9.8 meters per second every second. That is to say, if I threw up a stone at the speed of 9.8 meters per second, then after a second, it would have 0 velocity, because 9.8 meters per second would be taking off that velocity that I'm throwing the stone up with. Okay, so I do know that this acceleration is fixed. I have a formula for it. It's not dependent on time. It's always the same. Velocity is always reducing at minus 9.8 meters per second. It's always trying to pull this stone back down to the ground. So if I wanted to find velocity, I would need to integrate my acceleration with respect to time. Now, to integrate that, I've got my acceleration is minus 9.8. So when I integrate this thing, I get minus 9.8 t plus c, and that's equal to v. Now, I can work out what c is because I had this information up at the top here. So when the velocity is 4.9, that's just over here, and I've got minus 9.8 t, and t, by the way, there is 0. Got that. Okay, t is 0, and then I've got my plus c there. So you can see that c is equal to 4.9. So now I've got the formula for velocity. V is equal to minus 9.8 t plus 4.9. That's just me solving this equation here. That's a 0 there, by the way, not 6. So, okay, so that's me saying, well, this is 0, so c is equal to the 4.9. Okay, so there's my formula for velocity. What am I actually trying to find? By the way, I'm trying to find the maximum height reached by the stone. The maximum height, by the way, is here. It's when my velocity is equal to 0, or dsdt. So I could set this thing equal to 0. I set my velocity equal to 0 now. 9.8t plus 4.9. And I think the answer to that, if I solve that, you can do the solving, is 0.5. Okay, so after 0.5 seconds, which would make sense, wouldn't it? Because 4.9 is half of 9.8, so we will lose that in half a second, because we will lose 9.8 meters per second every second, so we will lose 4.9 half a second. Okay, so there's the first question. The second part here says find the speed with which it hits the ground. So we're looking at this, we're looking for the velocity, first of all, here. So the slope of this graph at this point here. Now we know that that's when displacement is equal to it's equal to 0. So we need to set S is equal to 0, but we don't have a formula for S. So we're going to need to integrate. Yeah, we're going to need to integrate here. Checking with the book. Oh, I never answered a previous question. Okay, I never finished this off. Now, just looking at the book, there was an extra part to this. Sorry about this. Find the maximum height the reached by the stone. We actually only found the time. We never found the height. Okay, well, we still need to do this anyway. To find the height, we actually need a formula for S, and S is d dt. Okay, I only found out the time at which I reached the maximum height. I never actually found the height. Okay, so I'm going to need to integrate minus 9.8 t plus 4.9 with respect. So if we do that, we've got minus 4.9 t squared. So that's me increasing the power by 1 and reducing by divided by my new power, plus 4.9 t plus c. And then we can use this information again in order to work out what the plus c is. So if we put in t is 0 and s is 2, then we should work out what c is. Now, I'm not going to do that. I'm running out of space here, but let's just check the book. When we check the book on this one, we can see they're doing exactly the same thing here. There's the formula. They've just said, well, the implication of this, and they've not really shown much working out here. They've put t is 0 in, s is 2, and they've determined that c is equal to 2. Obviously, in fact, because this becomes 0, this becomes 0, we just get 2 is equal to plus c. Okay, so just going back to this, so c is equal to 2. In this case, we've got s equals minus 4.9 t squared plus 4.9 t plus 2. Okay, so find the maximum height reached by the stone. Well, that happens after 0.5 seconds. So if you substitute 0.5 into that formula, you will get your displacement. Again, I'm running out of space. So in substituting in the 0.5 there, we'll get 3.225. Okay, so all that's happening there is we're putting in 0.5 seconds into the formula for displacement, and you're getting 225. Okay, 225. Okay, right. Second part of the question: find the speed with which it hits the ground. So actually, that's fairly straightforward now. The speed with which it hits the ground. Well, we know that the displacement is going to be 0 when it hits the ground. Here's a formula for displacement. So we need to set the s is equal to 0, which is what I was saying previously. If we set s is equal to 0, then we can solve the quadratic. When you solve the quadratic, you can just type that into your calculator, use your GDC for that, or your normal Casio will solve quadratics as well. And just looking back, you can see that's exactly what they've done, and they've come up with 1.31 seconds. And then they actually said, what's the speed with which it hits the ground? So you'll need to substitute the 1.31 seconds back into the velocity formula there. You'll get a negative answer because you can see that we have a negative gradient at this point. But of course, they're asking for the speed, so you'll need to change it into a positive because speed is the magnitude of velocity. Oh, that question was actually a little longer than I thought. So yeah, work through that carefully. There's a lot of information, but importantly, try and change the information at the start into this. Okay, so come up with your sort of information at the start in maths, and that's going to help you work out the C's in each of these cases. So the C for the velocity when we integrated the acceleration, and also the C for the displacement when we integrated the displacement velocity to get the displacement. Okay, and perhaps as well, a little graph of what's going on is useful. In this case, I used a displacement time graph as well. Okay, sorry about the slightly messing up in the middle there and missing out the second part of part A. Right, okay, let's look at example 20, and example 20 is the last example before 11J. So let's look at this one. So just take this. Okay. So this one says a particle moves so that its velocity at time t is given by the equation v equals 4t sine of t squared in brackets. And then it says, given that it is initially at the origin. So again, let's look at that. Initially means when time is at 0. Initially is the beginning. And at the origin means that your displacement is going to be 0 at that point. Find an expression for the displacement at time t. Okay, that's what we've got to do. So we know that we need to integrate the velocity to get displacement. So we're not being required to use differentiation again. We're again being required to use integration. Some of these questions could be differentiation. So let's integrate this then. So we've got the integral of 4t sine t squared with respect to t. There we go. Now, there's two parts to this, and we don't know integration by parts, which would deal with this in a different way, but we do know integration by substitution. Now, to be honest, with this one, I wouldn't do a substitution here. I would think, well, sine comes from cos. Remember that cos t, just pull this one up, would differentiate minus sine of t. Now, if you had cos of t squared, that would differentiate to minus 2t sine of t squared. Put that in brackets. Okay. So we know that because of the chain rule, because we know that we would have to differentiate cos, but we also have to differentiate the function inside the function, which would end up on the outside. And then I would think, well, that's almost the same as this, but I've just times this one by minus 2 here. So what I can do is I can make this minus 2 sine t squared with respect to t, and then I can just divide by a minus 2 there in front. Then that brings me to minus a half, and inside this integral here, we can see goes backwards to cos cos t squared. Oh, I've messed up again. Guys, I'm messing up today. Sorry about this. You see my mistake, by the way? I'm going to look. My mistake is there. Perhaps you can see what it is. Perhaps you can see that minus 2 and minus 2 times together to give 4, not minus 1, not 1 over minus 2. That would bring us back to 1, not 4. Okay, so that's pretty dumb of me. Sorry about that. Lots of mistakes today. Okay, so this one should be a minus 2 to make that the same thing. Sorry about that. So yeah, I'm glad I checked that one. So yeah, so if we then want to integrate this thing, that's the same as integrating this thing here, go backwards from the differentiation there. So we would have cos t squared, and then we would have a plus c on the end as well. Okay, now you can do this whole thing by a substitution, and your substitution would be that u equals to t squared, and then u dt is equal to t, and then you can replace dt, switch these two. You can replace dt by du over 2t, and when you replace that, you'll see that the t cancels there, and then of course this will become u. So you can do it like that as well. Okay, but that's techniques from before. Okay, so given that let's just see if we've answered the question. Given that it's initially at the origin, find the expression for the displacement at time t. So we have these initial conditions here. These initial conditions. So this is our expression for s. So if we put in now s is equal to 0, we've got -2 and then cos of 0 squared cos of 0 plus c. And of course, cos of 0 is 1, so -2 there. So c is equal to 2. So our s here is in fact -2 cos t squared plus 2. Okay, that's our formula for s. Now, note that previously, when we put in t is equal to 2 into a cubic or a quadratic, then your c was just 0 as well. Now, in this case, when we put in t is equal to 0, c wasn't equal to 0. Okay, so because when you put t into here, you'll actually get out t is equal to 0 into here, you'll actually get out s is equal to -2. Okay, so what I'm saying is that when time is 0, c is not always 0. Right, so that's answered the first part. The second part of the question says, find the time at which it returns to the starting point. The time at which it returns to the starting point. Now, at this point, I would use my GDC, and I think that's what they do in the book as well. Let's just rush this one a little bit. So there we go. We can say, we could actually come up with this graph, 2 minus 2 cos t squared. That's the same as my formula here. We can put that into the GDC by typing y is equal to this, change the t to x, and then we can find the zeros, what they're calling the zeros, the roots. So find out where it crosses the axis. So it's going to cross the axis here, 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 and here. So that's one way of doing it. The other way of doing this is if I just set s is equal to 0 here, I'll end up getting 0. I'll end up getting, running out of space, just trying to figure out how to write it down. -2 cos t squared plus 2. So if I take off the 2 and divide by -2, I'm actually looking for where is cos of t squared equal to 1. Okay, and if you look at the cos graph is at 1 at t is equal to 0, but also it's equal to 1 at 2 pi. So t squared has got to be equal to 2 pi. And if you take the square root of that, you get the answer, which they give you here, 2.51 seconds. Guys, that wasn't perfect today, but I hope that helps.